I'm sure there's no interruptions.
Okay, so ready?
We're
All
ready.
right, team, go ahead and get started.
All right. As our understanding of the universe expands, one thing still remains uncertain: the development of our home planet Earth. Billions of years ago, our solar system started to take shape, turning hot gas into the cores of the 8 planets we know today. Studying these cores could unlock the secrets to how early solar systems are formed. However, due to high temperatures and pressures, technology cannot observe Earth's core. With Earth's core out of the question, we must look to the stars in search of a proxy. Locked in orbit around the sun between Mars and Jupiter lies Psyche 16. Psyche is believed to be the remnants of a once developing planet. Early in the planet's development, Psyche was violently disrupted, hurtling its exposed core through space. In August of 2022, NASA will launch an orbital craft to study Psyche from afar. If this data comes back promising, a surface mission will be considered. With 1/70th of Earth's gravity, Psyche is considered a microgravity body. This introduces unique engineering challenges. Previous microgravity landers have struggled, and this struggle could lead to mission failure. This opens the door for new, novel ideas. Next slide. We are Team 1, Landing System for Uncertain Terrain. I'm Austin Nardi. With me today is Dutch Schaefer, Cameron Curtis, Chris Pryor, Tyler Harris. Our advisor is Dr. Allen, and here is a brief overview of our solution.
The Kinetic Energy Rebound System, a prototype rebounding landing system designed by our team at Michigan Technological University. In previous microgravity landings, the anchoring system has been a common point of failure, leading to undesirable rebounds that may jeopardize mission success. To address this, our team has decided to take a radically different approach and create a system that utilizes rebounding to its advantage, requiring no anchoring at all. Our design uses collision dynamics and energy transfer to create a controlled rebound scenario. By absorbing the potential energy of freefall into compression springs, there is a moment in time where the velocity of the payload is essentially zero. We release the package at this moment, leaving it safely on the surface while the rest of the lander springs away. Removing the external MLI coating reveals some of our key design features, such as the main thrusters, used for powered descent from orbit, the attitude adjustment thrusters, used to orient the craft normal to Psyche's surface, the pyrotechnic release pins, which allow for pinpoint accuracy in payload deployment, and our compression springs, which are the focal point of this rebounding design.
All right, with that, I'd like to give a brief overview of what we'll be discussing today. So our mission begins, we were commissioned by NASA and ASU to develop a system to deliver a scientific research payload to the surface of the microgravity planetesimal known as Psyche. We have been divided into 4 teams at Michigan Tech who are looking to develop a full system deliverable for sampling the surface. We are the landing team. We are also working with the robotic explorer team, the sampling system team, and the sample return team. Our mission is split into 2 distinct phases. We begin with a powered descent from the orbiter to a point just above the surface of Psyche, and then our solution takes over in order to safely deliver the package to the surface. To prove the feasibility of this concept, we have developed both physical and simulated prototypes in order to showcase the functionality of our design concept. Some of our engineering requirements that we have developed for this project. Initially, we set out to have our target mass between right around 450 kilograms. However, due to the fact that we are working amongst 3 other teams whose masses are also fluidly changing, we have exceeded this, but this is not beyond the realm of our system to adapt to. Additionally, we initially set out to have 75% of our payload volume or our total volume be available for payload. However, this is a very scalable value, and we have currently about 80% of the internal volume being usable. And then finally, we have the power draw of the electronics that we have designed for our full scale concept. However, these are simply theoretical values, as the components are likely to change should this be pursued further. Finally, for our scale to Earth prototype, we initially intended on having a 1/5 energy scale for our drop testing. However, due to changes in our mass and some physical limitations of the prototype that will be discussed later, this actually ended up being about 1/5, which was still an acceptable test for us.
So in order to get the project up and running, we needed to ensure that the concept we had devised was feasible. To do this, we started with hand calculations and then further went on to create simulations to verify those hand calculations. What we saw is that they were very similar, which was very promising for us in our work. So what you're seeing is a plot of the velocity versus time. And basically this was our proof that the velocity change is not instantaneous, like a lot of the research that we had been doing was leading us to believe. The velocity change happens over a certain amount of time that we would be able to go in with data measurement hardware and find the velocity that we needed and drop the payload. So using those simulations, we were also devising things like the spring constant that we would need, which is obviously a focal point of the design that we have here. So we went in and edited masses and things like that and came up with spring constants that we used to order the springs for the prototype. We also devised a release mechanism that used mechanical advantage so that the solenoids that we had purchased would be able to do their job effectively. And then we also used laser cut structural sheet components to ensure that our center of gravity requirements were being met, as well as our mass requirements. So this is the control system that we were using for our real life prototype. On the far left, we start with the accelerometer data that comes into a signal conditioning block. The signal conditioning block integrates that data, turns it into velocity, and that is then fed into our code trigger. The code trigger is there as just a safety mechanism to ensure that when the prototype is hoisted in the air, it doesn't accidentally detect that the velocity is 0 and drop the payload on anybody underneath it at the time. Once that trigger decides or sends the go ahead to the drop trigger, that is when the system begins looking for when the velocity is 0 after the system has been released. And then when it sees that it's at the designated drop velocity, it sends a signal to the motor index, and then that sends a voltage to our relays.
So as our system sends the voltage, as you can see in the schematic on your left, we have the beagle bone. The GPIO pin is the pin that sends out the voltage. It goes to a relay, which controls a 12-volt source power. Then we have our 2 solenoids tied in parallel so that they have the correct timing. On the right here, we have just a simple schematic of our release box, our control system box. And this really was just a point so that we had a little bit of safety measure so we weren't dropping the box unintended from our height. So our testing environment was up at the SDC. We would arrive and we would calibrate our beagle bone to the gravity. And then we would lift it up to the designated height for the day and we would drop it. As it came down and collapsed its springs, release the payload, we would then take the data from that, analyze it alongside slow motion video, and kind of customize our control system timing. We would then lift it back up and drop it again. So we have some data from our tests. Round 1 proved that we had a little bit of a structural issue, which we correctly fixed. Round 2, we were able to pull out usable data, and we dropped from 1.5 meters with 3.36 kilograms and an expected payload force of 6 Gs. If you play the video here, we can see it'll come down in slow-mo. And as it's coming down, our velocity goes up. We see the spike and we have a trigger. If you can tell, the payload was released just a little bit late. So while this was very promising, we needed further improvements. After observing a lot of our slow motion video, we noticed that we had a mechanical release issue. on the far left of your screen is a latch that was not, or that was fully unlatched while the right side was fully engaged still. This was causing our timing to be off and throwing our payload to one side. Go forward. So initially we had thought this was a fully mechanical issue. So we went through and we redesigned the payload hanger, we chamfered all the edges, and we increased our mass to our 1/3 requirement. But then we found out that we were actually having an electrical issue. So in the red circle here, we had tied those our solenoids in parallel, but what they were doing is overloading the relay that we had. So to solve this issue, we went back and we designated a single relay for each solenoid. Then we moved on to round 3 testing. This is again from 1.5 meters, but now we have increased our payload mass to 8.4 kilograms and an expected G-force of 9 Gs. As we come down, again, we see our velocity go up, we impact and we release, but again, it's just still too slow. So the red line here is our trigger, and we were triggering based off of velocity, but we were just still off. But this gave us a lot of confidence. So we decided to drop from our full 1/5 scale. And this is where we came into finding out we had some deformation issues. As this video plays, you can see the top of the plate deforming in. We kind of anticipated this through our FEA. If you play that video, oh, sorry. So through the FEA, and as that plate deformed, we were seeing about 1/4 inch of deformation. So we believe that this plastic deformation we were seeing was due to cyclic loading. But we got some very great results.
So the next step in the process was to add realism to our Psyche simulation. And to do this, we needed to look at the data we had from our actual test drops and compare that to data that we had from our simulated test drops. So here is 2 overlaid plots of similar drops in the simulation and real world environments. And we're going to look at 3 key components. So the first thing to note would be the peak velocities. Everything up until that point tells us that the physics in our simulation is working properly. We had very similar characteristics. And then the second piece that we'll look at would be the release triggers. You'll notice that the purple dotted line is the actual prototype drop trigger, and the red is the simulated drop trigger. The reason that the purple one is so much further ahead in time than the red drop trigger is because of the mechanical release timing delay that we have in the physical prototype. That is not something that we had built into the simulation, but that was a great piece for us to see to add realism to our actual simulation for Psyche. And then the last piece would be the rebound position. And you'll notice these are quite dissimilar. And this was an issue that we were also finding that when the beagle bone, if it were able to move at all inside of the housing that we had for it, it could skew our results pretty heavily, like you see here. So ultimately, we ended up using this data to add realism. We did that in a couple ways. The first, obviously, being we added all of the masses. We were working fluidly throughout the semester with other teams who were making design decisions right alongside of us. So once they had all their final masses, we were able to update our spring constant and put those masses into the simulation. We also were able to add things like energy losses. One thing that we were noticing through our testing was we were rebounding to about 70 to 80% of our drop height. So we took into account the energy losses that we were seeing with that, and we added things like coefficient of restitution to the Psyche simulation based off the predicted ground surface characteristics of Psyche. And then we were also able to add in the time delay that we were seeing. However, this doesn't really show itself in the simulation, as the time delay with our Psyche components was much shorter than the actual physical prototype.
All right, through this testing and simulation process, we did identify 3 major components to improve if we were to move from the alpha phase to the beta phase of prototyping. Mainly, the accelerometer that we use would need significant improvement to its sampling rate. The beagle bone was limited to 166 hertz, which significantly limited our ability to capture that inflection point during our testing. We would recommend improving this to anywhere upwards of 2000 hertz with improved sensors. Additionally, the delay caused by our mechanical release system caused for some timing issues. We had to build in a pre-trigger to account for the fact that we couldn't actuate our release as fast as we would like. So minimizing this value would allow for further capturing of that instant in time. And then finally, we would like to minimize the material deformation experience, both through improved materials as well as structural changes to the design of the prototype. We'd really like to minimize that value below a 1/4 inch of material deformation. So with that, we'd like to thank these individuals for their continued help through our process here in the program. We'd also like to thank all of you for your time and open up the floor to any questions.
All right, thank you, team. No for questions?
What's driving this increased cost for the second prototype? You're more than doubling the cost.
Yeah, mainly our control system. For our proposed version 2, we would like to use the CDAC, and we know that the school provides some CDAC and National Instruments software and hardware, but this was all brand new from NI's website, and that was about $4,000 of that cost. And that I don't know how much the school would allow for us to implement that, but if we were going to pay for everything straight off.
That's just to achieve the sampling rate.
Yes.
What is MLI?
Multi-layer insulation. So MLI it generally has a gold foil on the exterior, like you see on most satellites. Has several components on the interior below the gold foil that help protect from both the radiation experience in space as well as the extreme temperatures. And that would mostly be used to cover up any sensitive electronics or other components that may be sensitive to the temperature.
Space wrap.
Yes. Yes. Space aluminum foil, pretty much.
Do y'all have any ideas, any proposed ideas on how to mitigate that deformation?
So we were initially thinking if we had just more time in our testing process, we were actually considering welding on some steel ribs to the top plate to brace the flat sheet metal. That would help prevent some of that flexing that we experienced. Additionally, if we were to totally remake that component, probably using a thicker gauge of steel or higher strength. We were mostly using mild steel for the current prototype.
I thought I saw in the first slide, y'all are overweight a little bit.
Yes. So the values that you see on that slide are actually all 4 teams combined.
Okay.
Yes.
Yeah. So a lot of the initial requirements were developed before any of our teams had a solid image of what we were going to be constructing. And so those values were changing. However, because we are using the springs, those are highly tunable to higher masses. So this would be an acceptable weight even in our current design.
Yeah, you're looking for 0.03. You want to trigger in 0.03 seconds.
Mechanically, yes.
Yeah. What's the story behind that number?
So, oh, sorry, Chris.
No,
Okay, so we have identified that there's a pretty standard release pin that is used in space applications nowadays. It uses a pyrotechnic charge, essentially a small explosive charge, to pull a pin in a split second. And those, in the general rule of thumb that we found, could actuate in about 25 milliseconds. And so if we could simply use pulling those pins to be our release system, that's about the delay that we would be experiencing from when the control system says go to pins fully released.
Can I see the 2 overlaid, the simulation and the actual?
Keep going. It's quite a ways. Go back to. Oh, there you go. Yeah. If you have any questions, let me know.
Lots of information.
Yeah.
All right. Yeah, and then the wobbles, it just flying through
Yeah.
space.
In our simulation, it was the base of our lander vibrating back and forth, causing those.
Is that where you have your your sensor? Is it on the base?
No, so the in the simulation, the base kind of vibrates, but that also causes
The body.
small vibrations in the body. So it is sensing the body in the simulation. But the sensors are located up on the middle upper
You
plate.
suppose that lag there after the first drop in velocity is due to the rope?
Yeah, so we were dropping, and when it would rebound, we'd catch it with the rope. So that is a lot of the reason why we saw just the flat line after.
Okay.
But it is also due to just our sampling hardware.
Yeah, we primarily use the rope just to keep the testing safe and not.
Yeah. Makes sense.
Additionally, the beagle bone, once it impacted, it would measure fairly accurately up until our release, but once it got that rebound started, it would shift slightly in the housing, and all data from that point was kind of hit or miss.
Okay. Yeah, this is all really cool. I'd be proud of that simulation.
We are.
Yeah.
That's all the questions I had for now.
Any questions from our guests online?
I had one. I like this idea. It's a cool idea. It's got legs. And the one question I have is a series of questions, but it's centered around one thing. Everything you do is predicated on all the motion along one line, linear motion, and you're going to hit the base, you're going to hit your psyche surface all at the same time. So what happens? That's not going to happen. So what happens when you're coming down and one side hits a little rock or something, then you start to get some rotation, different vectors into your dynamic considerations here, and your release is going to be, it's going to be skewed off. You saw a little bit of that for a different reason in one of your videos, the last one where your payload was released way too late, but you saw some tumbling there.
Yeah.
But for a different reason, your legs are not going to hit all at the same time. And so this other stuff can be all tuned out. It can be developed, and you have some really quick sensors. And I'm just kind of trying to imagine what in the gravitational sort of conditions of psyche, have you done any thinking or put any thought into what time frame that event is going to span?
Yeah, so I guess to address the first in terms of the uneven contact, that was partially the large reason we went by a circular contact pad on the bottom of the springs, and that way, even when one side of the pad contacts before the other, all three of the springs would begin to deform at slightly different rates, which is something that we created some MATLAB codes earlier in the semester to address how long our springs would need to be to adjust for, let's say, a 10-degree slope. How much would one need to compress before the other side of the pad would contact? But in terms of the time frame, we would be looking at less than a second of contact time with the surface, even in the microgravity body. So the collision would not be as violent as our Earth testing, but the window would still be very small, and the amount of tumbling, it would have to be a pretty severe list in order for the craft to tumble.
And to add on to that, landing at an angle was something we had hoped to have achieved in our testing, but due to our deformation, we did not, unfortunately, get that far in our testing.
Yeah, that would have been nice to see. If you set it at 10 degrees and drop it, and then you'll see what I'm talking about. You can imagine what I'm talking about, I'm sure.
Absolutely.
But okay, thank you.
Yeah, thank you.
Absolutely.
I just had a thought of it would, right now all the supporting's on the outside and you drop from the inside. It would have been kind of cool to keep a hollow inside, like a pogo stick, and then drop from the outside.
Yes, ideally it would just be one spring.
Because you could still have the same kind of cushioning effect now from it or that.
Yeah.
that thing would just eject out the top, and then you kind of take this out of the equation.
Absolutely. That initially, one of my thoughts of that would be that the payload volume. I know the rover team is a fairly significant
Right.
solid body.
Can't put a hole in the.
Right. So they might have an issue with us boring a hole through them, but assuming that they could be flexible in that design, that would absolutely be something interesting to pursue.
All right, thank you very much, team.
Thank you.
Videos on point.
Yeah,
Thank you.
yeah, that's all cam.
I
So
don't know what software do you use there?
Vegas Pro.
Okay.
Yeah.
Yeah, that's solid.
Oh yeah, and the animation was done in Blender.
You should check out the
The Expo.
FPV.
Okay.
Yeah. Yeah, the animation took a pretty significant amount of time to render.
Like that, man.
People online, we're gonna mute video and sound for a moment, deal with what might be a couple technical difficulties. We'll be back in about 5 minutes.